Hi guys. So while I'm waiting for everybody else to show up, we're gonna I'll answer homework questions at the end of class today. I just want to make sure that we have enough time to make it through most of chapter 1.3. We'll see how we're doing on stuff. If we have time at the end, then maybe we can spend, like the last 5 or 7 minutes or whatever talking about homework problems. But you guys are welcome to come to office hours and ask questions about homework. That would be a great place to discuss it. Did everybody get the announcement and see on our Canvas page the detailed explanations? I put up a couple more homework problems up on there too, so you guys can have a chance to take a look at those. Also, the lecture videos are up there too. They're also on the YouTube page. So far, I've been able to add them without a problem. If you guys wanted to check those out as well, if you need it. Our quiz will become available today at noon. It'll be available from noon today until noon tomorrow. Okay, so a 24-hour window within which to start it. Okay, what's going to happen is when you open it up, when you have access to it, you'll have 30 minutes to actually complete it. Okay, but when you get it, there's a file download. Like you'll want to open up that quiz file, right? It's a PDF. Open it up, take a look at it. You don't have to print it out. If you do, that's great. It'll be easier for me to look at. But you can load it up on your screen, copy down the questions onto a piece of paper if you're not printing it out. Copy down the questions, work through your answers, and then when you're done, you'll have 15 minutes to take a picture or scan it in and upload a PDF to the web page, okay, to the Canvas page. Even though we're assuming that this is, we can't stop you from looking at your notes or your book or whatever, but we do ask that you're not talking to each other about the quiz or how to solve things or talking to anybody about how to do the assessments. And we're also asking you not to look at things like Wolfram Alpha or other online tutorials that are going to solve it for you, or if you use your calculator to solve things for you too. So keep that in mind. It's for you. We want to see how much you remember, how much you know about these things. Okay, so and also I just want to mention too, if you have any problems, this is my first time using Canvas this semester. If for some reason the quiz doesn't become available or you can't access it or whatever, send me an email and I'll see what I can do about the Canvas page. What is the question? Can we submit a picture of the quiz to Canvas or does it have to be a PDF? So PDF is my preferred format. If you absolutely cannot convert it from some picture to a PDF, I will also accept a JPEG, but I can't read other file formats. The PDF is the easiest one for me to take a look at and to grade. So please, I ask you be kind and use a PDF format. I think that there are free PDF converter apps out there, so that in case you're using your phone, you can, I think there's a download. I don't care if it says at the bottom, this is used by Cam Scanner or whatever. I don't care if it has anything like that at the bottom. So you're free to use one of those free programs that'll convert it for you. But it must be PDF or JPEG in order to upload it. All right. So let's get started and talking about what we need to talk about. This is continuing on chapter 1.3. So last time we left off with talking about continuity. We're talking about discontinuities in our functions. And we were starting to get into the hang of it, using limits to help us define whether a function was continuous or not. Okay, and knowing a function is continuous is a really important concept, because if a function is continuous, there's a whole bunch of stuff that I can actually do with that function. I can do all sorts of, math processes on it. I can evaluate it. If it's not continuous, I have to think about it very differently. Okay, so we talked about one-sided continuities, and we talked about left continuous if my left limit is equal to the function evaluated at that let's see, okay, so somebody is referencing on the chat, the Office Lens is a good app. It does a good photo to PDF. Great, that's good to know. Let's see. So and then it could be right continuous if our function evaluated at that point is equal to our limit as we come in from the right-hand side. Okay, so when we talked yesterday, we did this piecewise function. Piecewise functions are great for looking at things, that change at transition points. And so when we looked at approaching at these transition points, we approached x equals 1. Okay, you can see as I'm approaching it from the left-hand side, okay, my function's actually defined, right? My function is defined that's going to be equal to my right-hand limit. Okay, so my right-hand limit and my function are equal to each other, but my left-hand limit will exist, but it's not equal to the function value. So we say It's discontinuous because the right and the left-hand limits are not equal to each other. Okay, that's rule number one. The other one is that my function is not equal to my limit. Okay, but we say because the right-hand limit is equal to the function evaluated at that right-hand side, so we say that this function is right continuous at x equals 1. When we look at x equals 3, we did this yesterday. When we look at x equals 3, which is our other transition point, okay, we look at coming in from the left-hand side, coming in from the right-hand side. My function, my limit exists. It's equal to the same thing on the left and the right. And my function is actually defined at that point, and it's equal to my limit. Okay, so because my left and the right and the function all have the same values, okay, we say that this function here is continuous at x equals 3. We can also see on our graph here. Okay. So that was example 12, where we were starting to use the concept of a limit to help us evaluate continuity on a function. Okay, so we're going to continue our discussion about continuity and functions and stuff today. Okay, a little bit. There we go. We're going to continue on that discussion today. There's a lot of definitions that I need to cover. It's going to be a little boring as I go through all those different definitions, so bear with me as we do that. But we're going to be, those definitions will give us a vocabulary that we can then use to describe other things later. Okay, so we talked about jump discontinuities, removable discontinuities. One of the last kind of discontinuities I want to talk about is called an infinite discontinuity. We looked at some infinite discontinuities, you know, and I think it must have been yesterday or Monday when we talked about especially vertical asymptotes. So for example, I've got some kind of a vertical asymptote here, say at x equals c, and my function, you know, cruises in and it hits this asymptote on the left and the right. My function then cruises on up to positive infinity because I've got this vertical asymptote in my function itself. So that's where it's going up to both positive infinity, but at x equals c, I could also have a rational function where it goes to positive infinity on one side and negative infinity on the other. Okay, rational function like this. These are infinite discontinuities, right? Where my function tends up to the infinite. We can also get what's called a one-sided. This is a one-sided infinite discontinuity. We'll call this x equals c. So I've got my function, it comes in, it does something, and then it's actually defined right here, defined right here, but coming in from the right-hand side, my function does something different. These are often, we can use these in piecewise functions. Okay, so to talk about infinite discontinuity in words, I'll write it down. We'll say at x equals c, it's got an infinite discontinuity if one or both of the one-sided limits is infinite. Excuse me. And then we say that this has an infinite discontinuity. Okay. These are both. Okay, and this is a one-sided. Okay. All right, so we've talked about our different types of discontinuities. Okay, our jump, our removable, and now our infinite discontinuity. Okay. All right. You guys all got that before I turn the page? Okay, so I need to go into a whole bunch of definitions. It's you don't have to bear with me here as we talk about all these different definitions. It's not going to be the most interesting thing, but once we get the definitions down, then we can go back into working through examples. So we want to do is we want to talk about how we can build continuous functions. Our whole goal. We want things to be continuous because it's easier to work with continuous functions. Okay, so I've got a bunch of theorems that I need to put up. So my first theorem, we've got some basic laws of continuity. Okay, so theorem 1 talks about these basic laws of continuity that we're going to discuss. Okay, so basically, first off, I want to be able to define if I've got these two functions, f of x and g of x are continuous. Now remember what it means to be continuous, right? To be continuous is on a function, I've got both my left and my right hand limits are equal to each other, and so the limit exists at x equals c, okay? And that function evaluated at x equals c is equal to the limit, okay? That's how we define whether or not a function is continuous. At x equals c. Okay, so I've got f and g, they're both functions, they're both continuous at x equals c. I'm going to do a bunch of mathematical properties on them: addition, subtraction, multiplication, all sorts of stuff. And what we're saying is when we do these properties, the resultant function that comes out of that is also continuous. So the first thing I'm going to do is I'm going to add or subtract f of x and g of x. F of x plus g of x, if f and g are both continuous, adding and subtracting these two continuous functions is still going to be a continuous output. This is all assuming that we're looking at x equals c. K is some constant. Right? If I multiply k times a function, right, it isn't going to change its continuity at all. I multiply f of x times g of x. Okay, if f and g are both continuous, multiplying them together is going to give me a continuous function. F of x divided by g of x. Okay, this is also going to be continuous if we can also say that g of c is not equal to 0. Remember, we're evaluating things at x equals c, right? We're looking at the continuity at that spot. So you have to make sure that we haven't introduced a domain restriction there. Okay, so all of these function properties, all of these functions are going to be continuous too. Okay, our second theorem we're going to do is polynomial and rational functions. Okay, let's talk about it. So we're going to say let p of x and q of x be polynomials. Okay, then what's going to happen? So p of x is continuous on the real number line. Okay, it's a polynomial, it's got some stuff going on, it's continuous. You can say p of x divided by q of x, our rational function, is continuous on its domain. Okay, so that means that we have to look at where is q of x, where are the zeros of q. So that means it's continuous on its domain, which means it's continuous at all values x equals c, such that q of c does not equal to 0. Oops, sorry, can't say that. Okay, so we're looking at where are the places that q of x has zeros, right? And then we have to include those in our domain restrictions so that we're not introducing discontinuities. But we're saying elsewhere, okay, this function is continuous. You guys good with this page here before I move it? All right. Our third theorem, okay, is we're talking about some basic functions. We're going to work through some of these basic functions here. Okay, so the first basic function, y equals x to the 1 over n. This is like I'm doing an nth root of x, right? So this is one of our basic functions. This is continuous on its domain for n being a natural number. our root. Our next, sine of x and cosine of x. Okay, sine of x and cosine of x, they don't have any domain restrictions at all. They're perfectly continuous. On our real number line. Okay. These are building blocks for other things. Okay, y equals b raised to the x part. This is our exponential function, our basic exponential function. We often think about y equals e to the x, e meaning like 2.718, so on and so forth. Okay, so b is any base, right? I can use any value for that. So our basic exponential function, this is continuous on the real line for b greater than 0, and also b not equal to 1. B equaling 1 doesn't give us like a domain problem, but it's not a very interesting function, and it's certainly not exponential. When b is equal to 1, 1 raised to the x power is just equal to 1, so y equals 1. It's just a straight line, okay? So it's a continuous function, but it's just not exponential anymore. Lastly, y equals log base b of x, okay? This is continuous for x greater than 0, for b greater than 0, and b, of course, not equal to 1. So these are, basic functions. We're going to make up, more complex functions out of these. Like we're going to talk about trig in just a sec. Okay, so using quotients. So for continuity, use the continuity law for quotients to help me define my trig functions. Remember, our tangent function is sine over cosine. Our cotangent function is cosine over sine. Okay. Our secant function is 1 over cosine. And our cosecant function is 1 over sine. So these are quotient, right? I have to, sorry, this is a fraction. I have to watch out, where is the cosine equal to 0? Where's the sine equal to 0? Those are going to have infinite discontinuities when I have cosine and sine equals to 0. Okay, so when we talk about continuity for these functions here, we're saying that we have continuous on their domains where the denominator is non-zero. Okay, these functions have infinite discontinuities where the denominator is equal to 0. Remember your graphs for tangent and cotangent, secant, cosecant. Okay, we're going to have infinite discontinuities as we head up towards these vertical asymptotes where cosine and sine are equal to 0. But otherwise, the functions themselves are continuous. Okay, give you guys a second to finish writing that. You guys all set with that? Okay. Fourth theorem, I know these is a lot of theorems to think about. Our fourth theorem, we have inverse functions. Okay, continuity of inverse functions. Okay, so we want to first talk about our function itself. If f of x is continuous on some interval, I'll call the interval big I, okay? And it has the range, capital R, right? So my function f of x has a domain and range. But in terms of inverse functions, I'm really interested in the range of my function here. So, and if the inverse of this function exists, then the inverse function is also continuous with domain equal to what used to be the range. Remember when we have a function and we take its inverse, right? We swap the x and the y. So we're switching the domain and the range. This is why we were thinking about the range only when we thought about our function originally. So if I can take the inverse, if I can get an inverse, then the inverse is going to be continuous, and it's going to have a domain equal to what used to be the range of the original function. Okay, my fifth theorem. I know this isn't the most interesting thing to write down all these definitions, but it's helpful to have them out there. We're going to talk about composite functions. Remember composite functions, f composed of g. We have a function nested inside of another function. Okay, so we say if g is a function, and this function is continuous at x equals c, and we have another function f is continuous at x equals g of c. So think about it this way. I've got some function g of x, right? So I've got g of x, and g of x at some x equals c, it has a value, right? So g of c, right? So whatever that value is, I plug that into my f function, okay? So if f is continuous at that new value, x equals g of c, okay, then we can say the composite function big F is equal to f of x is continuous at x equals c. Okay. We do these all the time, right, with our functions. So I've got some function that looks like, say, for example, big F of x equals x squared plus 9 to the 1/3, right? I'm building up. This is my composite function. So something, this is continuous because it's a composite function. The composite function, and my inner function, so this big, the outside function, oops, f of x equals x to the 1/3 is continuous, and g of x equals x squared plus 9 is also continuous. Okay, so that's how we're thinking about it. We've been composing functions all the time. Maybe we didn't call it a composite function, but this is how we think about. We take, elementary component pieces and we build up more complex functions out of it. Which leads me into the next definition here. It's part of the composite function. You've got these things that are called elementary functions. Elementary function is a function that is constructed out of basic functions using addition, like x squared plus 9. I'm adding those two basic functions together. Subtraction, multiplication, division, and composition. Right? We do this all the time. We build up more complex functions out of really simple pieces. So an elementary function itself is continuous on its domain if the basic functions are also continuous. Right, so if our component pieces are continuous and I make something bigger, right, out of that, then my elementary function is also going to be continuous. I'm going to think of that as going back to that first theorem that we talked about, where if I add two functions together, x squared plus 9, x squared is a function, 9 is a function. 9 isn't a very interesting function, right? But it's still a function, right? I'm adding those two together, but they're both independently continuous, right? So I should get a continuous function out of it. Okay. Okay, so I'm just gonna, you guys have this here before I put it away. Okay, so let's talk about some basic things that we can do, and we'll get back into doing some examples. So let's talk about substitution as a thing that we can do to help us evaluate limits. Okay, so let's see. So how are we going to evaluate limits? So let's say, for example, I've got limit as x approaches c of some function f of x. Well, I'm just going to substitute in. Everywhere I see an x, I'm going to plug in my c, right? So we're just going to substitute. We're going to plug in c for x, and we're going to evaluate our function, okay, because we can. So let's take a look. So our first example of doing that is example 13, right? So the limit as x goes to pi over 3 of sine of x, let me write this a little bit better, goes to pi over 3 of sine of x. Okay. Now, sine of x, we said before, was continuous, right? I don't have any domain restrictions, so I can just simply plug in sine of pi over 3. Okay. So whatever, I'm going to evaluate that function at, and I'm going to get radical 3 over 2. That's going to be my limit. You can imagine our sine function as we approach pi over 3 from both sides, it's equal to radical 3 over 2. Okay, same thing for part B. Let's write this a little bit nicer. X goes to minus 1, 3 to the x all over x plus 5 square rooted. Okay, so let's take a look. I'm heading towards x equals minus 1. Well, if I plug in minus 1, I'm not going to introduce a domain restriction, right? I won't have a divide by 0 or a negative in the radical. So just doing a raw substitution is going to be fine. Everywhere I see an x, I plug in a minus 1. Right? 3 to the minus 1 makes it 1/3. This is 1 over, this is radical, minus 1 plus 5 is equal to 4. 1 over radical 4 is 2. It's equal to 2. So 1/3 times 1/2 is 1/6. Because all I did was substitute because I could. I didn't have to worry about like a domain restriction, you know, it's causing a divide by 0 or other problems. Okay, so I could just plain old substitute it. And that's usually your first step. When you look at limits, you think, I just substitute it in there. If you can, you should, because that's where our function is approaching, and then I want to get a value for what that's equal to. Okay. So another method that we can do is I'm going to evaluate my limit algebraically, because substitution may not work, right? If I substitute it, maybe I'm going to introduce a domain restriction or a problem. I can't do substitution directly. So we're going to evaluate our limit algebraically. So I'm going to do that here on example 14. So I've got this evaluating, so I want to look at the limit as x goes to 4 of this function here, x squared minus 16 all over x minus 4. So when I first look at it, right, if I substitute in x equals 4, I'm going to get a 0 in the denominator. So I have to avoid that. So I always like the graphs. I like to see what's going on here. So I'm going to go, here's 4. Sorry, here's 4, here's 8. I want to graph it out and see what this thing looks like. So how this looks is, I have a problem at x equals 4. I've got a hole there, right? So looks like this. You can graph this out on your calculator. If you graph it on your calculator is just going to show you a straight line. It's going to look completely fine, like a linear graph. But the problem is mine won't show me that there's an open circle here, okay? Unless I say specifically, when x is equal to 4, what is y equal to? And then it will give me back nothing. It'll say y equals blank. okay? So what's happening here, algebraically, I'm going to rewrite this limit, x minus 4. So I'm going to factor this out. So it's x plus 4, x minus 4, x minus 4. Okay, so now what we're going to do is, this is what we call removable discontinuity. I'm going to pretend to cancel, okay? So I'm going to I'm going to put it in quotes, cancel x minus 4. Right? I'm not really canceling it because it's a part of my function, so I can't get rid of it. It's actually, this is what my function is. Okay, but it's a removable discontinuity because to evaluate it, I pretend to cancel it out. So if I cancel it out, then I'm left with the limit as x goes to 4 of simply x plus 4, in which case I can do substitution. It's going to be 4 plus 4, which is equal to, oops, sorry, you can't see anything. 4 plus 4 equals 8, which we can see on the graph, right? As I approach 4, x equals 4 from the right-hand side. As I approach x equals 4 from the left-hand side, I'm approaching, right, y equals 8. Okay, so this is what we're getting here. So this is an algebraic method, right, where I can pretend to cancel out my domain restriction, where so then I can actually just do substitution. Okay, but we're not changing the function, but it's just going to help us evaluate it. Now I want to note, using the idea of limits, that this function is not continuous. Let's talk about that for a minute. My left-hand limit is equal to my right-hand limit. That's true. But my function evaluated at x equals 4 is not equal to my function at x equals 4. Okay, so my limit is equal to 8, but my function is not defined at x equals 4. Okay, so that means that this function here, by our definition of continuity, is not continuous. Okay, because I can't get a function value out of it, even though I can get a limit. Okay. You guys all see how we're analyzing and processing this function here. Okay. All right. So let's talk about called an indeterminate form. Okay, so the indeterminate forms, right? So at x equals c, if the formula for f of c, f of c yields something like this, right? If I plug in, x equals c, or I get some kind of a limit, I do something, and I get, let's say, 0 over 0, or I get infinity over infinity, or I get infinity times 0, or infinity minus infinity, just as some examples, right? All of these things here are what we call indeterminate. If you're not sure, but you find yourself scratching your head going, well, I have a 0 over 0, so which one dominates? Is the numerator, is this thing equal to 0, or is it the divide by 0 error that causes the problem? If I have infinity over infinity, I can't cancel those out and just get it equal to 1, right? I mean, which one goes to infinity first, right? Is this thing equal to infinity, or is this equal to 0? Same thing here, is this equal to 0? Like, if you find yourself scratching your head wondering how you're going to evaluate this, right? Take a step back, because it's probably an indeterminate form, okay? So when we have an indeterminate form, we need a different strategy. We want to transform. We're going to learn more about indeterminate forms as we go, but it's important to start thinking about it now. So we're going to transform our function into a new form that can be evaluated by substitution. Oops, sorry. Substitution. Okay. So we'll do some examples so you can see what I'm talking about here. So indeterminate form, we have to have some strategy for how we handle it. But being able first to recognize that we're dealing with an indeterminate form is important, okay? Because that's going to allow us to do some stuff later on. Okay. So now, right, this is example 15. We want to evaluate this limit. X squared minus 4x plus 3 all over x squared plus x minus 12. Okay. So the first step that we're going to do in our transformation is I want to factor the numerator and denominator as a first step. Okay, so I'm going to say it's still taking the limit. X goes to 3. So when I factor this out, if you're in doubt about how you're factoring, do the quadratic formula. Okay, or you can plot this and find the zeros on your function and that'll give it to you. But make sure when you factor it out that you do a really quick check. Okay, just a quick FOIL out check. So x squared minus 1x minus 3x positive 3. Okay, that's going to sum up to this polynomial here. X minus 3, x plus 4. Do a quick check. X squared plus 4 minus 3x minus 12. Okay, so I factored it out correctly. And I know it sounds like, why am I belaboring this point? Because I have seen so many times on exams, people factor things out incorrectly, and then the rest of the answer is wrong, even though like the math, the calculus will be correct, but the factoring will be incorrect. Okay, so just do a really like a 5-second check to make sure that you factored it correctly. Okay, so I factored it out, right? So now, if I were to just to do, if we do substitution here, right? If I plug in 3, x equals 3. If I plug in 3, then I'm going to get an indeterminate form. Which is 0 over 0, right? So I'm going to get x minus 3 all over x minus 3. It gives me 0 over 0. That's my indeterminate form. X equals 3. Okay, so this is part of our strategy. We knew this was the example was going to work with that. So what we're going to do is we're going to cancel out. I put that in quotes because we're not changing the function. We're just helping. We're doing something as a trick, a strategy to help us evaluate it. So we're going to cancel out our common factor, which in this case is x minus 3. Okay, so if I cancel that out from top and bottom, then my limit now looks like this. My limit, x minus 3, looks like x minus 1 all over x plus 4. Okay. Like if you graph this out on your calculator, right, you're not going to see x equals 3 as a discontinuity. Your function, your graphing calculator isn't going to put a nice little hole there, even though it should. It's just going to make it just straight. And then you'll have to say, if you say x equals 3, what's my y value? My calculator will come up blank. Okay, so it's a removable discontinuity because we pretend to cancel it out. Okay, so like I'm going to pretend to cancel that out like that. Okay, so I get this. Okay, now my third step is I can evaluate this new form by substitution. Okay, so I've got the limit as x goes to 3, oops, x minus 1 all over x plus 4. And I can just substitute, so it's going to be 3 minus 1 over 3 plus 4, which is 2 over 7. Okay, so as we head towards x equals 3, our function, right, our left and right hand limits are heading towards the value of 2 over 7. Okay, so this is a strategy for helping us deal with an indeterminate form. Okay. You guys will have this before I turn the page. Okay, we'll try some other indeterminate forms too. So example 16, we want to evaluate this limit as x heads towards pi over 2, tangent over secant, right? So let's just remember what things are. So tangent is our sine of x over cosine of x. So at pi over 2, right, you may remember our cosine of pi over 2 is equal to 0, right? So I've got a problem. So I have a 0, right, in my numerator. So this one here, I've got secant. So then my tangent of x, so tangent of pi over 2 is equal to, it's an infinite discontinuity. It's a vertical asymptote. You guys will see, I can't see that on the screen. That's a little bit better. Right, can't tell if it's going off the screen now. So my secant of x is equal to 1 over cosine of x, again at pi over 2. My cosine of x is equal to 0. So my secant of x is equal to infinity. This is our vertical asymptote. again, for our secant function at pi over 2. So tangent and secant both have vertical asymptotes at pi over 2. So that means when I take the limit as x approaches pi over 2 of tangent over secant, I'm dealing with an indeterminate form, right? I've got it's heading towards infinity in numerator, heading towards infinity in the denominator. Okay, so I'm going to do our strategy, right? So the first thing I'm going to do is I'm going to factor. It looks like I'm factoring, but I'm taking the tangent and the secant down into its component pieces. So it's going to look like the limit as x goes to pi over 2 of, let's write it in pieces, sine of x, cosine of x, all over, this is my secant, 1 over cosine of x. Fraction divided by fraction, that's cosine of x all over 1. So now we're dealing with the limit, the limit as x goes to pi over 2 of, right, simply sine of x, which doesn't have a problem, okay? So this is our second step. We're canceling. We're going to cancel out that part, right, that repeated part, and I'm going to rewrite it, okay? And now I can evaluate by substitution. Okay, so I'm going to go the limit as x goes to pi over 2 of sine of x is equal to the sine of pi over 2, which is equal to 1. Okay. So some strategies for handling indeterminate forms. Do another example. You guys all set with this example here? Okay. So example 17 is going to be a case of another indeterminate form. So look at what's happening if I just do substitution. If I plug in x equals positive 1 in here, I'm going to get this is equal to 1 over this is going to infinity. This is like a 1 over 0 minus 1 over 0, which is I'm basically looking at infinity minus infinity. It's undefined, okay? So this is also indeterminate. Okay, so I'm going to do my, they both have discontinuities at x equals 1. Okay, so let's do our steps. Okay, so I'm going to transform algebraically. And then I'm going to cancel out repeated factor. Cancel out my terms. Okay, so let's go ahead and take a look at that. So I'm going to take this out of context here. So 1 over x minus 1 minus 2 over x squared minus 1. Okay, which when I go to take a look at what am I actually trying to do here, I'm going to try to combine this stuff. So if I look at this is x minus 1, x plus 1, I'm going to think about my common denominator, right? This is my common denominator, which means I have to multiply this side here, top and bottom, by x plus 1. So x plus 1 to find a common denominator, okay? So when I do that, I'm going to get x plus 1 all over minus 1 plus 1 minus 2 all over x minus 1, x plus 1. Okay, now they have the same denominator. I can bring them together. So I'm looking at x plus 1 minus 2 all over x plus 1, x minus 1. Okay. Now I can simplify this out, right? So when I combine all like terms, I'm going to get x minus 1 all over x plus 1, minus 1. Okay. In parentheses to give us a clue. Now we can see, right, I'm going to cancel out, pretend that I'm canceling out that repeated factor. Okay. So now what I'm left with is the limit as x goes to 1 of 1 over x plus 1, which doesn't have a discontinuity at x equals 1. But that's still there in the function, right? It's still there in the function. I just like figured out a way algebraically so that I can process this. Okay, so now our next step is to evaluate this limit. We're going to substitute, evaluate the limit by substitution. So the limit as x goes to 1 over x plus 1 equals 1 over 1, which is equal to 1 over 2. So we're trying to come up with tools to help us evaluate these limits, right? When just pure substitution isn't going to work. And we're dealing with cases like this one where I have indeterminate forms, okay? So if you find yourself scratching your head going, okay, well, is it infinity minus infinity? What does that equal to, right? So take a step back and think about the tools in our toolkit for being able to evaluate that function. Okay. You guys, you good with this page here? Right. The thing about indeterminate forms that I want to point out, what is not indeterminate is if I have some number, like a 3 or a 5 or whatever, and that's being divided by 0. Okay, this is just undefined. Okay, so some number divided by 0 is not indeterminate. It's just an undefined value, right? We have a divide by 0 error. Okay, the indeterminate form is when I have 0 divided by 0, or if I have infinity divided by 0. Okay, so which one is going to dominate, right? Which one's going to work? If it's just some number, right, like 10 divided by 0, that's just undefined. Okay, so be very careful. Okay, so make sure that you're not mistakenly processing something as indeterminate when it's actually undefined. Okay, how you guys doing so far? There's a lot of information in this class, in this particular chapter section. Okay, let's see. There's some stuff I want to talk about when we get into the, let's see, how do I describe this? We have some theorems that I need to put out that are also going to give us some toolkits in addition to some stuff about trig. We'll see how far I get into it, and then maybe I want to stop in the next 5 minutes or so and see if you guys have any questions on homework problems. Okay, so let's just talk about, there's a theorem called our squeeze theorem. That's a Q, our squeeze theorem. And it's sort of, squeeze theorem gets used actually a lot in calculus too. It helps us evaluate certain functions. So let's talk about what that means. Let's say I've got a bunch of functions here. So I've got my regular function. Here's f of x, right? And then I've got other functions. Let's see, I'll draw it in different colors. Got another function. U of x, and I have another function, L of x, right? So I've got these 3 different functions, f of x, u of x, and L of x, but f of x is the one that we're trying to evaluate. So our squeeze theorem says, if our function f of x is what we consider like trapped, it's bounded, but it's trapped between 2 other functions. In this case, we're calling them u and L of x, okay? And this is on some interval, I, okay? So now what we can say is, if L of x is less than or equal to our function, which is less than or equal to u of x, okay, for all x values that are elements of our interval. So for all x inside of our interval, f of x is greater than L, right? We can see it here, and it's less than u. We can see it here. Okay, so f of x is bounded on the top and bounded on the bottom by these 2 different functions. Okay. This theorem applies, or squeeze theorem applies when f of x is squeezed at points x equals c, okay, within our interval. Okay. Now we can use limits. So if we say the limit as x approaches c of L of x is equal to the limit as x approaches c of u of x, and that's equal to some value, some L value. Okay, maybe we don't know what f of x is. F of x is maybe undefined. So f of x doesn't have to be defined at x equals c, right? But we can use these other functions. Usually L of x and U of x are more simple functions, okay? But we know, one of them is greater, one of them is lesser, one of them is like lower, one is upper, right? And that their limit converges, both of them, their limit converges to the same value at this point, x equals c, right? F of x doesn't have to be defined there in order for us to use this squeeze theorem to say we're going to be able to define what f of x is. For this to be true, the limit as x goes to c of f of x, it's going to equal to L. Okay, so we're using the fact that we know what u of x is and we know what L of x is to help us come up with a definition for what f of x is as x approaches c. That's our squeeze theorem. Okay. And it's something that it gets used a lot in other stuff. Let's see, do I have, I think, 18. Yeah, so example 18 uses our squeeze theorem for it. So let me, let's see, I think, yeah, I think maybe what I'd like to do is, I can do this on, I can finish up this part on Monday, okay, to actually go through it, because to actually process and to discuss this example 18 is going to be a little bit longer. Okay, so we'll pick up this on Monday, okay, we'll work through the rest of the examples, and then we'll wrap up chapter 1.3. We'll maybe be able to start 1.4 as well, okay? So I'll stop there, and then I'll open it up for you guys if you have questions on the homework, okay, or if you want to ask me things that you maybe are worried about for the quiz today. Anybody have questions they want to ask for the homework, or on the homework, or for the quiz? Let me bring up, I don't know if people are writing to the chat. Is the quiz, do you mean calc as in calculator? Is that what you're talking about? You're free to use you're free to use your calculator. In theory, most of this class can be done without the calculator, but I find the calculator helpful for graphing things. So definitely you can use your calculator on it. I think you probably have all the skills you need so that you probably don't need the calculator, but you're free to use it. Anybody have a specific homework problem they want to ask about? You can put it into the chat if you don't want to say it out loud. Everybody's good? Y'all have it? All right, ask about my calculator, enunciate it. I think she asked about a Casio. The university recommends this, so in case you don't have a calculator already, they're kind of giving you some ideas about which calculator to buy. If you have a Casio and you're already familiar with it, go for it. I'm not going to care. I think you just want to make sure that you're not using it. Like, I think some of these more recent calculators, you can plug in the function and actually have it do it for you, which we're not going to be very happy about. It's going to become obvious in subsequent semesters that you just basically relied on your calculator to solve everything for you. So you'll want to make sure that you're solving the problems yourself. Okay, and so the answer is yes, you can use whatever calculator type you want. It doesn't have to be a TI, just so long as you're doing this stuff yourself. Okay. If nobody has a question on any particular homework problems, then we can stop here, and you guys can use this time to review stuff or do other things. You're free to come to office hours. Like I said, the quiz will become available at noon. Okay. If you have a problem, or if it somehow isn't accessible, or isn't, you can't download the document or take a look at what it is, send me an email really quickly so that I can get online and fix it. Okay. Okay, guys.
I
Nobody.
have a quick question. Sorry, I have a quick
Okay.
question.
Right.
So, well, do you think by doing this homework it'll be satisfactory enough as like studying and then reviewing the like lectures, or do you think that there's any like additional problems or review that we should be doing?
You know, that's a great question. I personally think that the homework is an excellent preparation for the quizzes, certainly, because the quizzes are based off of the homework, and it's an excellent prep for the exams. The homework problems are, you know, kind of very interesting problems to take a look at. So yeah, if you can do the homework problems, you're in a really good position for mastering the quizzes, definitely, and then certainly mastering the exam as well. Yeah.
Okay, thank you.
Yeah, you're welcome. Okay, guys. Nobody has any other questions, then I'll end the meeting. And then you're free to come to office hours if you think of a question later. Don't forget the exam, the quiz does cover part of like just the beginning part of chapter 1.3. So keep that in mind for when you're studying. And I'll take that part of the homework. You can pass in 1.2, 1.1, and then just the first, I think, 5 problems of 1.3 I'll collect for homework today. Okay? And those are due at midnight tonight. Okay, guys. Have a great day.
Thank you.
Thank you.
Bye.
Thanks so much.
Bye. Take it easy.